Yesterday, we'd gotten as far as talking about the four-chambered heart, and we'd gotten as far as laying out the chambers, and we'd begun to describe the cells which are involved in lining the chambers, forming the myocardium, and we just started on the cell layers of the mesothelium, which are going to form the pericardial sac. We'll begin today with that same idea. I'll make a crude drawing of the heart and walk our way through these different layers. But as we walk our way through this, recognize that the endocardium is a layer of cells. It's a single layer of cells. And these endocardial cells go throughout the cardiovascular system. It doesn't matter whether we're talking about the atrium or the covering on the valves, or whether we're all the way out in the vasculature talking about the capillaries. There's always a lining of those vessels formed by the endocardium, a single layer of endothelial cells. The next layer beneath the endocardium, which of course is going to line the chambers, is going to be the myocardium. The myocardium is just the muscle. It's a pretty thick piece of meat. It's constructed from cardiomyocytes. We'll talk about the details of the cardiomyocytes here in a few days, but right now we're simply going to talk about this as the muscular wall. And then on the far side of the muscular wall, going from the chamber to the endocardium, to the myocardium, to the far side, there's now a new layer of cells. This cell layer will be the mesothelium. The mesothelium will look an awful lot like an epithelium and be a continuous layer of cells. It will have a basal lamina. The basal lamina is going to attach these mesothelial cells to the wall of the heart. But what's now different about this is that this layer of mesothelial cells which are attached to the wall of the heart will then extend out into the space between the heart and the body wall and then move around and attach to the body wall. So that we'll end up with something called a parietal pericardium and a visceral pericardium, these two layers. But between the two layers is going to be an open space. It's going to be a sac called the pericardial sac. And the pericardial sac then is going to contain fluid. Because if you can picture the drawing of the heart from yesterday, when the blood flows into the ventricles and expands those ventricles, the heart wall has to slip along the body wall. And when the myocardium contracts and forces the fluid out of the chambers, then the volume of the heart becomes smaller. So throughout life, there's this continuous expansion of the heart and contraction of the heart. The heart then has to slip along the body wall, and the slippage along the body wall is largely lubricated by the fluid inside the pericardial sac. This has some clinical meaning. Turns out if you get too much fluid inside the pericardial sac, then pressures build up and you have a hard time filling the heart. And we'll talk a little bit about that kind of pathology. But that will bring us to two major definitions you have to be fluent with when we talk about the heart. The first is something known as diastole. Diastole is a fancy Latin word which simply means filling. Diastole is the period when the chambers of the heart are filling with blood. So diastole is low pressure filling of the chambers. There's a point we reach where we have filled the chambers with blood, and this point is called the end diastolic volume. We'll then see at the point of end diastolic volume, we begin the contraction of the myocardium. The contraction of the myocardium to generate force on the fluid in the chamber is said to be systole. So diastole is filling, systole is contraction. Diastole is a period of relaxation, dystole is a period of contraction. Diastole is a period of filling, systole is a period of contraction. Ventricular myocardial contraction. So that's the definition. But to really recognize how the heart's working, we can lay this out in something known as the cardiac cycle. And the cardiac cycle could be described in a really, really simple diagram. And if you understand this diagram and you understand what's going on at each point in the diagram, you pretty much understand how the heart functions. And what we'll see is that there's a period of myocardial contraction. This is said to be the period of isovolumetric contraction. This means the volume is not changing, but the contraction of the muscle is generating more and more force. That force increases and increases until a point where the pressure on the chamber side is greater than the pressure on the far side of either the pulmonary or the aortic valve. When the pressure on the chamber side is greater than on the far side, that valve swings open. There's nothing fancy about these valves. They're nothing more than doors, and those are doors that respond to pressure. And so we're going to open the aortic and pulmonary valves by the pressure generated by the contraction of the myocardium. When the valve swings open, when the doors swing open, then the fluid leaves the ventricular chamber, both the right and left ventricular chamber, almost simultaneously. The fluid then is forced out into the tube. This is the period of ejection. You're ejecting the fluid from the chamber. This goes on until the pressure on the far side of the valve is greater than the pressure on the chamber side of the valve. When the pressure on the far side of the valve is greater than the pressure on the chamber side of the valve snaps shut. When the valve snaps shut, then relaxation begins. There's a period of isovolumetric relaxation. Isovolumetric tells us the volume's not changing. The muscle is relaxed. And at this time, we begin the process of diastolic filling. So the cycle begins again. And one of the ideas here that we'll emphasize is that when the myocardium has contracted and those sarcomere lengths have shortened, that now in order to start the cycle again, we have to reset the lengths of those sarcomeres. When we talked about this in skeletal muscle, we talked about antagonistic muscles. So that I use my biceps to bring my hand to my shoulder. When I want to extend my hand, I then have to contract the triceps, reset the sarcomere length in the biceps, and extend my hand. So we have these antagonistic muscles that we contract, and when we contract one muscle, we reset the length of the sarcomeres in the antagonistic muscle. We don't have an antagonistic muscle in the heart. The only force that we can use is the diastolic filling. So what we're going to use is the force, the low pressure return of blood flowing into the atria and then into the ventricles to reset the sarcomere length. So during the period of diastolic filling, we'll reset the sarcomere length. And once they're reset and we begin the contraction, we start the cycle all over again. As we work our way through the cycle, one of the ideas that will come forward is what's happening to each of the valves. Again, I can't emphasize too much. These valves are nothing fancy. They're just doors. They're just mechanical structures. And so we'll see that during the period of diastolic filling, when the blood is flowing into the atrium and into the ventricle, those floppy AV valves are open. But when the isovolumetric contraction begins and the pressure on the fluid increases, that's going to snap shut those AV valves. They're not very strong. So basically, they're kind of floppy, so they snap shut. The aortic and pulmonary valves are much stouter, and so it takes much, much greater pressure to open them. So we increase the pressure, increase the pressure, increase the pressure, until such time those stout valves open and the blood leaves. Then, when the pressure on the far side is greater than on the chamber side, they close. And we see this cycle over and over again, and we'll walk our way through what this means. One of the ideas that will come out when we draw the cardiac cycle is that the heart pump is not a particularly efficient pump. That is, it will bring in with each cycle of the heart about 120 mils. So at the end of diastole, the chambers of the heart will contain about 120 mils of fluid. But then after the contraction and after the ejection phase, there still remains behind about 50 milliliters. So we'll have an end diastolic volume, typically of 120 mils, an end systolic volume, typically of about 70 mils, and the difference between the two is said to be the stroke volume. Cardiac output then is defined as the stroke volume times the cycles per minute. And we'll work our way through the numbers, and it's an astonishing number. When you get around to the numbers, every minute of every day of your life, just sitting there quietly, not including times of exercise, at 70 beats per minute, at 70 mils for each cycle, you're pushing almost 5 liters of blood through your heart every minute of every day of your life. It's a busy heart. And when that stops, you're done too. So let's start here with the image we had last time. This is the right atrium. This is the right ventricle. Remember, what we were looking at in that open region is the chamber. So this is all open chamber. This is also open chamber. And then this thin structure we talked about last time, we labeled this as the atrial myocardium. And we labeled this as the ventricular myocardium. And we emphasized yesterday that these are two pumps laid out in series. This right heart was said to be the pulmonary pump. And the left pump was said to be the systemic pump, but it had pretty much the same components. If we put the inputs and outputs, up here is the vena cava. Coming out of the right ventricular chamber is the pulmonary artery. Again, the convention carrying blood away from the heart is the pulmonary artery. The blood then is brought back into the left atrium through the pulmonary vein. And so this is the left atrium and the left ventricle. We said that there were a set of valves. We said there was a set of valves on the right side, known as the right AV valve, also known as the tricuspid valve. And on the left side, there was the left AV valve, also known as the bicuspid or mitral valve. In each case, the flow of fluid is in through the vena cava, across the AV valve, and then subsequently, when the pressure is generated, out across this structure here, known as the pulmonary valve, on the right side, and on the left side, out across this structure, known as the aortic valve. And the blood flow through the system we described yesterday was in through the atria and out from the ventricle, all those through the chambers. And where we closed was trying to describe the cellular structure of the heart. And when we look inside the chamber, the wall of the chamber is lined with a continuous layer of endothelial cells. These valves, too, are lined with endothelial cells, and the continuous layer of endothelium extends out into the aorta. It extends into the pulmonary vein. It extends into the right and left atria. It extends into the pulmonary artery. It extends to be a lining of the right ventricular chamber. Wherever you look, these structures are lined by a single layer of cells called the endothelium. And it doesn't matter whether you're in the heart or whether you're out in the most distant structures of the cardiovascular system, there will always be a lining of endothelium. And in fact, once we get out into the exchange vessels, we get out into the fine structures of the capillaries, those capillaries are composed only of a single layer of endothelial cells. So this is said to be the endothelium. Now, you'll recognize the structure of the endothelium as being really similar to an epithelium. It's a single layer of cells. It's attached to the underlying structure by a basal lamina. And what, in fact, distinguishes the endothelium from an epithelium is the endothelium never extends to the outside world. Whenever we talk about an epithelium, we have to be able to find a route that goes to the outside world, whether it's the lining of the exocrine pancreas or what have you. Those epithelial cells are a continuous layer that goes to the outside. These never go to the outside. They're always confined within the cardiovascular compartment. Then this structure here is the wall. This is the myocardium. So that the endothelial cell lining, the lining of these cells, separates the blood in the chamber from the muscle cells of the myocardium. So we always have a layer of cells separating the blood from this muscle cell layer, the myocardium. Now, if we look carefully at the myocardium, we'll see that the myocardium is composed of millions upon millions of individual cardiomyocytes. We'll see a little later, all of those cardiomyocytes are linked one to the next by gap junctions. I'm going to simplify that a whole lot to try to conceptually say how we're going to generate force here, and remind you that these cardiac myocytes also contain a sarcomere. And that the structure of the sarcomere is really pretty much like the structure we talked about in skeletal muscle, where there are these thin filaments. And the thin filaments, again, are composed of actin, filamentous actin, troponin C, and tropomyosin. The story is pretty much the same. And then in between reside the myosin, thick filaments. So the myocardium, the wall of the heart, is simply muscle. And it's muscle that obeys all of the rules we learned previously, where calcium is released from the internal storage compartments, calcium binds to troponin C, moves to tropomyosin, the myosin head moves up, contacts the actin, and through a power stroke, again, ADP and PI leaving, we see the contraction of the muscle, the shortening of the sarcomere. The story is pretty much the same as for skeletal muscle. What we're doing when we shorten the sarcomeres is we are generating a force. Sarcomere shortening generates a force. You can read pressure on the chamber contents. The chamber contents, of course, is blood. So when we generate this force, we're going to put pressure on the blood, and we'll talk about this in a moment, what that's going to do to the valves. Before we get to the mechanics of all that, there's another cell layer I want to put on here. I'm going to wish I left more room down here. There's now going to be another cell layer. I'll put this in orange. And the cell layer here is of mesothelial cells. The mesothelial cells are attached to the substrate, just like the endothelial cells, just like an epithelium, so that there will be a basal lamina. And so the mesothelial cell layer attached to the external myocardium. Is called the visceral pericardium. So there's a layer of mesothelial cells stuck to the wall of the heart. We name that the visceral pericardium. But this layer of cells continues all around the heart and loops back on itself. And again, these mesothelial cells sit on a basal lamina. They sit on an extracellular protein matrix. That extracellular protein matrix now attaches the mesothelium, or the mesothelial cells, to the body wall. This layer of mesothelium attaching this layer of mesothelial cells attaching the pericardium to the wall of the body is said to be the parietal mesothelium. Well, more accurately, it's called the parietal pericardium. So what I'm trying to convey here, and it's true all the way around the heart, is that there's a layer of mesothelial cells attached to the external wall of the heart, but there's also another layer that loops back and attaches to the body wall. The upshot of all of this is that there's an open space between the apical surface of the mesothelial cells of the visceral pericardium and the parietal pericardium. And these mesothelial cells will in fact secrete fluid. They'll secrete fluid which are rich in polysaccharides, so they're slippery. And so now what we have is a sac. You can even think of it as a plastic bag. You can imagine the heart fitting down inside this plastic bag with this layer being attached to the wall of the heart. That would be the visceral pericardium. And the other side would attach to the body wall over here, and that would be the parietal pericardium. But in between, there's an open space, the pericardial sac. And that pericardial sac is filled with fluid so that when blood fills the chamber and it extends, the heart wall can slip along the body wall by using the slippery fluid inside the pericardial sac. Then when the heart contracts and becomes smaller, it slips back in the other direction. So the pericardial sac plays this important function of being filled with a slippery fluid so that every time your heart beats, it slips easily without much friction along the body wall. Well, in some cases, there is pathology that develops here. And the pathology is sometimes known as chronic pericarditis. Now, I bring this up not so much to point out the pathology of the heart, but to point out how the heart works. What happens in chronic pericarditis is the pericardial sac fills with fluid. So now we begin to fill up what's effectively a balloon, the pericardial sac, with fluid. The next piece you have to know about is that the blood flowing in from the lungs into the left side, or the blood flowing from the systemic vasculature into the right side, this return is a low pressure return. Typically, the pressure of the blood coming back into the heart, this low pressure return, the low pressure return is in terms of 3 to 10 millimeters of mercury at most. Now, this term, millimeters of mercury, is arcane. We don't use it in any other place anymore. But what it simply says is there's only sufficient pressure to raise a column of mercury that has a centimeter squared surface by a couple, 3 millimeters, 3 to 10 millimeters. So it's not a big pressure. We'll see the pressure that's generated on the aortic side, particularly, will be over 100 millimeters of mercury when we eject the blood from the heart. So this is a low pressure return. The importance of that is that if we have a low pressure return, bringing the fluid into these chambers, and simultaneously we begin to fill this bag, the pericardial sac, with fluid, because it's a confined space. If we start putting fluid in here, we can get concentrations of fluid in here so high that we now begin to generate pressures on the outside wall of the heart that are comparable to 3 to 10 millimeters of mercury. If the pressure out here equals the pressure filling the heart, there ain't no filling. If the pressure is greater here than here, there's no filling at all. And so it doesn't take much in the way of fluid inside the pericardial sac and an increase in pressure in the pericardial sac that you will restrict the diastolic filling phase of the heart. That becomes really, really dangerous, because if you consider you have to beat your heart 70 beats per minute all the time, or you don't get enough blood to your brain, if this pressure increases, if you don't get blood in, you can't pump blood out. So it becomes really dangerous if you get high pressures inside the pericardial sac. Emergency room physicians are trained to recognize this, whether it's by auscultation or by an echo. And they begin to see this problem, and they will take out a really gigantic needle, and they will immediately puncture your chest wall and insert that needle into the pericardial sac and draw out fluid, because you need to reduce that pressure immediately before the pressure in the pericardial sac increases beyond the pressure in the chambers. Simply to point out that the flow into both the right and left ventricular chambers is a low pressure return. And it doesn't take much pressure outside that region to be greater than that low pressure return. So any questions up to there? If not, let me show you a couple of pictures. This first one is just a much better picture of a fish. But again, the emphasis here was on the idea of a fish having a two-chambered heart. The idea that there was the receiving chamber, the atrium, and the ventricle, which pumped the blood throughout all of the vasculature of the fish. And we said here that the ventricle would pump blood first across the oxygenating organ, the gill. And that there were gill capillaries whose endothelium was right next door to the epithelium of the gill, so that oxygen could easily diffuse out of the water and into the blood, or alternatively, CO2 could diffuse out of the capillaries and into the water. And then the pressure generated by the ventricle, that pressure had to force the blood not only through the gill capillary network, but all the way through the capillary networks throughout the body. It would seem an inefficient system. And in fact, it wasn't efficient enough to support life on land. And so once life on land, and particularly homeothermic animals such as birds and mammals, began to develop, we formed a four-chambered heart. Now, if you go through the embryology of this, it's an exquisite system. You start out with a tube, you form an atrium and a ventricle, and then it folds over on itself and reproduces this four-chambered heart. But the four-chambered heart is nothing more than two pumps in series, and that's what's shown in this figure. This is an important figure. It's simple, but it's really important. It shows the right side of the heart here. This is receiving blood through the vena cava. It's coming across, as it comes in, it's coming across the right AV valve. And then when the myocardium contracts, it's going to force the blood out over the right, out across the right pulmonary valve, or the right semilunar valve, and out into the circuit of the lung. So this is now going to be the pulmonary artery carrying blood away from the heart and to the capillary system of the lung. Then in the capillaries, the blood flows through these very fine single endothelial cell layered structures called the capillaries. And at that site now, oxygen diffuses out of the air and into the blood, and we reoxygenate this deoxygenated blood. The oxygenated blood then now leaves the capillary beds of the lungs and comes back to the left pump, the other pump in series. Comes back through the pulmonary vein into the left atrium, across the left atrioventricular valve, also known as the bicuspid or the mitral valve, and then out across the aortic valve and into the aorta. And then the aorta will have branches and branches and branches, branches of arteries and arterioles, and they too feed a capillary bed. That blood flows through the exchange vessels called the capillaries, is drained then into the venules and veins, and goes back into the vena cava. So this is a closed system. The blood always, always, always remains within the chambers of the heart or within those tubes, never escapes. And what's more is, since there are these two pumps in series, that the volume of blood leaving the heart on the left side has to be equal to the volume of blood leaving the right side. Those two volumes need to be the same. Otherwise, we run out of blood. So that's the structure of the closed system. The next figure is showing what we just drew on the board. Now, it doesn't show the endothelial cell lining of the chambers or the valves. It doesn't show the mesothelial cell lining of the outside of the myocardium, but it shows nicely the four chambers. Over here, the right atrium, the right ventricle, and the flow of blood down across the atrioventricular valve and then out across the pulmonary valve to the lungs. The blood then coming back through the pulmonary veins into the left atrium, across the left AV valve, also known as the mitral valve, into the ventricle, and out across the aortic valve to the systemic vasculature. So that's the pathway. And the final figure I have here is just to point out what's meant by the mitral valve. This is a picture of a basically it's a grave. This is inside Exeter Cathedral. And this guy was the Bishop of Exeter until 1419, and they put him here. He's been lying there ever since. And this is the mitre. He was a bishop. And so this is the bishop's mitre. And if you look at this, you can see these two leaves. You can imagine the blood flowing from his head out across these two leaves, and these would be the mitral valves. So with that, any questions to there? Yes?
So I just go back to the fish real quick. Do you think that's because there's, being inferior, not being able to climb on land? Do you think that's also due to the pressure of the water assisting the intake of, two-chamber heart versus four-chamber heart?
I think that the existence of a two-chambered heart in the fish has to do simply with not needing a system to have two circuits. And they just may not be that metabolically active. Now, I'm kind of questionable about that, because if you start thinking about tuna and such, the tuna are really metabolically active. And they have special regions which called the rete mirabile. And the rete mirabile are special regions which are, I think they are specialized regions for exchanging oxygen into the tissues, particularly into muscle. So they have specializations to do that. They have adapted to higher metabolic activity, but they haven't changed their hearts. Squids change their hearts. The change in hearts first occurs in amphibians. And there you see a three-chambered heart. There are the two atria and the one ventricle. And then in reptiles, you begin to see a septum, a wall beginning to form between those two chambers and the two ventricular chambers. Now, the septum gets to the point where it's fairly efficient. You don't get much blood mixing between the right and left ventricles in a lot of these reptiles. But then once we begin to see birds, and I suspect if we had a soft body fossil of many of the dinosaurs, you'd see the same thing. We'll see a four-chambered heart. And that simply, presumably, is so you don't get any mixing of the deoxygenated and oxygenated blood in those ventricles. And in some cases, there are birth defects where you do get mixing, and those have to be fixed. But the why questions are always difficult. Anything else? Well, if not, let's leave this. It's a little messy, but let's leave it. And then over here, I'm going to put up a graph. And the graph is going to be the graph of the cardiac cycle. And the cardiac cycle graph is also known as the pressure volume curve. This pressure volume curve is going to simply have an axis and an ordinate. It's going to be unusual in comparison to a lot of the graphs that we put on the boards here because there's no time. So if we draw it this way, we see on the axis there's volume. And on the ordinate there's pressure. And typically the pressures are given in millimeters of mercury. We'll start here at point A. We'll label this as A. If we drop down and look at the volume here at point A is typically about 50 mils. If we come over to the ordinate, the pressure side, typically the pressure here is 3 to 10 millimeters of mercury. So it's a pretty low pressure. Now, there's now going to be this straight line. Comes across. And right at the end, there's a little bit of a bump. The line between A and B. A to B represents the period of diastolic. Filling. So you'll notice here that the volume is increasing. It goes from about 50 to about 120 milliliters. So effectively, we're going to be filling, we're going to be putting blood into the ventricular chamber. And we're going to talk about this for the left side because the pressures that we generate on the left side when we open the aortic valve are in terms of 100, 110 millimeters of mercury. When we open the pulmonary valve, those pressures are in terms of 30 to 40 millimeters of mercury. So we're going to talk about here the left side. But now we see that we're filling the ventricle. Now, notice that there's no change in pressure. Remember, this is the pressure on the ordinate. There's a bit of a change in pressure here. So we got a little bit of pressure right at the end before reaching the period known as end diastolic volume. In numbers, the end diastolic volume is 120. But note here there's a little bit of pressure. Where's that pressure coming from? Well, remember what we're doing is we're filling this chamber with blood flowing first into the atrium and over the atrioventricular valve. As the blood flows over the atrioventricular valve and fills the chamber, we get an increase in volume. But this is low pressure filling, so we don't change the pressure. Where the pressure begins to increase is that little bit of hump at the end where the atrial myocardium contracts. And when the atrial myocardium contracts, it's going to generate a force on the fluid inside the atrium. The rules will be the same as down here for the ventricle. It's just there isn't all that much muscular wall in the atrium to generate very much force. So we have this final push of fluid from the atrium into the ventricle. That's the final push of volume here into the ventricles. And there's a little bit of increase in pressure. Now, right here at point B, signals begin arriving at the muscle cells in the myocardium, in the ventricular myocardium. So at point B, ventricular myocardial contraction. Begins. In other words, at point B, we begin to shorten the sarcomeres. As we shorten the sarcomeres, we generate a pressure, a force on the fluid contained within the chamber. So the pressure now begins to go up, and that's shown here. So here in this line, we now see an increase in pressure, and the pressure increases and increases and increases until we reach the point here of point C. This period between point B and point C is said to be the period of iso, meaning same, volumetric. So note that there's no change in the volume. So this is isovolumetric contraction. So to take this image and apply it here, the period of isovolumetric contraction is after the blood has come across the AV valves and filled the ventricular chamber. And now the pressure begins to build because we have contraction, of shortening of these myocardial sarcomeres. That's going to increase the pressure here. Remember, we've come to the end of filling. So we have these fairly loose, floppy valves called the AV valves. What's going to happen when the pressure inside the chamber begins to increase? What are we going to do to those valves? We're going to close them, snap them shut. So these valves snap shut. Then the pressure increases and increases and increases, but there's no change in volume. So that's a period of isovolumetric contraction. But then up here, at point C, at this point, the aortic valve opens. So now we want to think about what's going on here at this interface, the interface between the blood in the chamber and the blood out here in the aorta. We've snapped shut the AV valve so no blood can be regurgitated back into the atrium. But now pressure is building on this valve. When the pressure in the chamber, so if we can say this pressure of the chamber, or let's say in the ventricle, is greater than the pressure in the aorta on the far side of the valve swings open. It's just a door. And there's a real world analogy to this, and it happens to be in this building. And many of you have experienced this, where after class you go to walk out of the building, and you come to that breaker bar on that door, and you think, I'll just open this thing, and you start pushing on it with your arms, and nothing happens. And then you decide something else has to change, and so you get behind it with your feet and your legs, and you force the door open. What you're doing is the same thing that's happening here. When you open this door, because the pressure inside the building is less than the air pressure on the outside, there's a considerable atmospheric pressure against that door. For you to open that door, you have to generate more force on the inside of the door than the air pressure on the outside of the door. When you overcome that pressure, you could open the door, and you'll notice that the air comes rushing in there. Well, it's just the opposite here. Here you increase the pressure, increase the pressure. The first part is you put your arms into it. Then when these sarcomeres get shorter and shorter and the pressure increases, they pop the valve open. When the pressure on the ventricular side is greater than the pressure on the aortic side, the valve opens, and blood now goes out across the valve. That process begins at C. At C, the aortic valve opens, and we see now the pressure drops. We see the pressure goes up, but the volume drops. So remember, this is the volume part of the curve. So this is telling us that we are swishing the blood out from the chamber out into the aorta. And the volume of blood in the the volume of blood in the ventricular chamber is becoming less. Now at this point, at point D, at that point, let me put it up here. At that point, the pressure in the aorta is greater than the pressure in the ventricle. So at this point now we have greater pressure on the far side of the valve than on the chamber side of the valve, and that snaps the valve shut. And if you're listening to a heart, you'll know, we all know this, there are two sounds. There's the lub sound and the dub sound. The lub sound is actually the first closing of the AV valves. So when you hear that lub, it's actually a representation of the closing of the valves. Turns out it's actually a vibration that's set up through the entire column of blood when this snaps shut. That's the lub sound. And then there's a period, if you have really good ears, you can hear a whoosh as the blood goes out into the aorta. And then following that, when the pressure in the aorta is greater than the pressure in the ventricle, that pressure closes the aortic valve and you hear the dub. That's the snapping shut of the valve. And people who are really good at this can hear heart sounds that represent problems with the valves, whether it's a leaky valve where blood is regurgitated back into the atrium, or whether it's what they call a stenotic valve, where it's narrowed and there's a lot of whoosh of fluid over the aortic valves. Cardiologists who are trained to do this can hear these differences. It takes years, but you can hear the differences. But a point here is that now at point D, the pressure in the aorta is greater than the pressure in the ventricle, the valve slams shut. And then there's this very brief period between point D and point A. And this is the period of isovolumetric relaxation. The period of isovolumetric relaxation is pretty short. And what's happening during the period of isovolumetric relaxation is that you're no longer sending signals, and we'll talk about the signals later. You're no longer sending signals to the myocardium to tell it to contract. This brings us back to the idea of antagonistic muscles. Remember, we said, if we talked about the antagonistic muscle of the biceps and the triceps, that I can contract my biceps and pull my hand up to my shoulder. And that's shortening the sarcomeres. But to reset the sarcomere length in my biceps, I have to contract the triceps and extend my arm. So we have antagonistic muscles in the skeletal system to reset muscle length. We don't have that here. So what are we going to use to reset the sarcomere length? We're simply going to use the low pressure return. Fluid is going to come into the ventricles, and it's going to distend the ventricle and stretch apart these sarcomeres. So now we're going to reset the length of the sarcomeres simply by allowing the fluid to come into the chamber. So we relax, we stop signaling contraction, and then from there all the way to B, we're using the lack of contraction to fill the ventricular chamber. And that's the period of diastolic filling. Now, there's a point here I want to make. That there is a volume. There's a volume between this point here of the end systolic volume. Label this as the end systolic volume. And this volume here called the end diastolic volume. This number, to give it a number, is typically 120. And in between is the stroke volume. The stroke volume is equal to the end diastolic volume minus the end systolic volume. And the stroke volume then, if to put numbers to this, is 120 minus 50, which is equal to 70. So the stroke volume is typically about 70 mils. That's with each cycle of the heart. But there's also, along with this, let me put it on the upper board, along with this is the concept of the cardiac output. And the cardiac output is the stroke volume times the cycles per minute. And to give you a number, if you think of stroke volume as being 70 mils times, say, 70 beats per minute, every minute you're that you're sitting there quietly, you're pumping almost 5 liters of fluid through the heart. What we'll talk about tomorrow is something called Starling's Law. And Starling's Law simply says the more blood that comes into the ventricle during diastolic filling, the more that will go out during systole, and we'll describe that tomorrow.